In this video, we're going to talk about how to make comparison of a pair of molecules to decide whether or not they're isomers and what sort of isomers. I think you'll find it helpful to have a chart such as what's shown in front of you in order to make these sort of comparisons. And so the idea here is if we're thinking about isomers, isomers are different compounds that have the same molecular formula. Now, there are different ways that compounds can have the same molecular formula and yet be different. One of the ways is structural isomers, and the other way are stereoisomers. Now, structural isomers are also known as constitutional isomers, whereas stereoisomers are also known as configurational isomers. Now, structural isomers have different attachment of atoms. In other words, they will have a different four-part name. So if you look at the example here, we have butane and then we have methylpropane. Literally, they have a different attachment of atoms. Now, another way we can have different compounds with the same molecular formula is we can have these compounds have different arrangement in space. And there are two ways that this can happen. There are the diastereomers and the enantiomers. Now, the enantiomers have a very specific definition. These are non-superposable mirror images. For our purpose, we'll be looking whether or not our compounds have a chiral center. And therefore, if they do have a chiral center, it's possible that we have a pair of enantiomers. Now, in terms of diastereomers, the only type that you're responsible for this year are the EZ type. Those are the ones that have carbon-carbon double bonds. However, diastereomers are more broadly defined as any kind of stereoisomer that's not an enantiomer. So there are other ways of having diastereomers, and if you go on to study organic chemistry, in second and further courses, you will see these cases. Again, for our purpose, we're looking for those carbon-carbon double bonds and the potential for an EZ type of diastereomer. Now let's keep this chart in mind as we make a couple of comparisons. One of the things that I'd like to mention, though, before we go on, is it's not possible if you decide that a pair of molecules are structural isomers for them to also be stereoisomers. So the thing that you should check first is, do you have structural isomers? And if you decide that there's the exact same attachment of atoms, then consider the possibility of stereoisomers. So let's look at our first pair of molecules at the top of this slide. You can see that the central carbon is attached to a bromo, chloro, fluoro, and hydrogen. Therefore, they have the exact same attachment of atoms. It's not possible for these to be constitutional or structural isomers. They potentially can be enantiomers. Now, obviously, they can't be diastereomers because they don't have the carbon-carbon double bond structure. To decide whether or not these are non-superposable mirror images, rather than try to rotate the molecules all around, I'm going to assign absolute configuration. So to do this, I'm going to prioritize according to atomic number. So we have 1, 2, 3, 4. And then over here, 1, 2, 3, 4. Now, unfortunately, the lowest priority group is not going back, and we need that in order to assign the absolute configuration. So I'm going to switch the hydrogen's priority with the fluorine's priority. And now the lowest priority group is going back. I count 1, 2, 3. And as such, I'm counting counterclockwise. Because this is counterclockwise after the switch, the original must have been clockwise. And therefore, the original must have been R. So once again, I count 1, 2, 3. This is counterclockwise. The original must have been clockwise, and therefore R. In the molecule on the right, again, the lowest priority group is not going back, so I'm going to switch 1 and 4. So 4 is going to go over here, 1 is going to go here, and now I'm going to count 1, 2, 3. So I count here in the counterclockwise way, so the original must have been clockwise, therefore the original, once again, must have been R. We would conclude, therefore, that these two structures are identical. Moving on to the next example. Now I see I have carbon-carbon double bonds, and so at first impulse you might think that we have the EZ type of diastereomer. But I'm going to number my carbons 1, 2, 3, 4, and 5, and then over here, 1, 2, 3, 4, and 5. Now I can see that in both cases, we have a double bond on carbon number 2. But on the left-hand side, my methyl group is on carbon 3, whereas on the right-hand side, my methyl group is on carbon number 2. Therefore, these have a different attachment of atoms. Because they have a different attachment of atoms, they are structural isomers. So I don't even consider whether or not they're stereoisomers, because if they're structural isomers, they can't be stereoisomers. Now, the structure on the right, in fact, doesn't have a diastereomer because it's not possible to prioritize about carbon number 2. There are 2 CH3 groups on either side. But the structure on the left does have a diastereomer. And right now, we can prioritize to see which one we have of the 2 diastereomers. So I'm going to prioritize about this carbon number 2, and I'll change my pen color here. So this is going to be 1 because carbon will beat hydrogen. And now I'm going to look at carbon number 3, and I'm comparing a CH3 group to a CH2CH3 group. And so the higher priority is the one that's further up. And once again, just to highlight this idea, I've got a carbon and a carbon. Now the bottom carbon is attached to 3 hydrogens, whereas the top carbon is attached to a carbon and 2 hydrogens. So of course carbon number 4 has a higher priority. So the 2 higher priorities are on opposite sides of the double bond, therefore this is an E structure. I can write the Z structure, and the idea is that you switch either the 2 groups that are on carbon number 2 or the 2 groups that are on carbon number 3. So for instance, if I go like this, and I have my double bond here, and then put this carbon down here, you say, well, how can I switch the 2 groups? Well, if I put my hydrogen down at the bottom and put my methyl group or the CH3 group up there. So 1, 2, 3, 4, 5, I've got 5 carbons. In terms of prioritizing, now I'll go back to my red pen. I have 1 up here, I have 1 right there, they're on the same side, so that is my Z. I hope you have found this short video in reviewing thinking about isomers to be helpful.